Welcome back, students. In the last lecture, we came up for an expression that relates the energy of a particle to the probability of observing a particle at that energy. This is the preliminary form of what will become the Boltzmann distribution. Today, we will continue to explore this topic and determine how dominant the Boltzmann distribution is and what the final form of the Boltzmann distribution is. And this is the all-important relationship of energy to temperature. So the learning goals for today are going to be to explain the dominant configuration and what we mean when we use these words, dominant configuration. And then we're going to connect the energy to the microstates available for a system, both in terms of the Boltzmann distribution, and also there's a link between the weight of the system and the energy that that system has. At this point, the book goes through a derivation for the dominance of the Boltzmann distribution. And what this means is it's a way to say how likely we are to measure the Boltzmann distribution compared to some other distribution. We're not going to go through that derivation in too much detail here, but we're going to simply state the results. In a very sort of pithy way, we can say that the Boltzmann distribution is very dominant. Now, what do I mean by this? So to check the dominance of a distribution, we can go back to our coin flip example. We might want to know how likely are we to get 5 out of 10 heads compared to 6 out of 10 heads. To do this, we simply compare the weights of both of these outcomes. Now, this is exactly the same as if we were to try to say, how likely am I to observe a particle in the first excited state compared to the ground state? We did that a lot last semester. What we did there is compare the Boltzmann distribution, and remember that those are simply ways to get the weights, the ratio of those two things. So we can compare the weight of state 5 over the weight of 6. So we have 5 heads, 6 heads. To calculate the weight of 5 heads, we take 10 factorial divided by 5 factorial times 5 factorial. And for 6, we do 10 and then over 6 and 4. This gives us 252 over 210 for a ratio of about 1.2. So what this means is that we have a 1.2 times more likely that we're going to see 5 out of 10 heads than 6 out of 10 heads. So for this case of 10 coin flips, we're not really that much more likely to see 5 heads as compared to 6 heads. We're slightly more likely, but we're probably going to see both of them. We can't really calculate these things for larger numbers, and this is what the book goes through an approximation that we can use. And if we have large numbers, we can calculate that the ratio of 2 different weights, and in this case, we're mostly interested in the maximum weight, the dominant distribution, compared to some other distribution, is approximately e raised to the n times the alpha RMS squared, where this alpha parameter talks about how wide the distribution is, and then you divide that by 2, and n is the total number of objects that we're measuring this for. So for our 10 coin flip example, n is equal to 10, and the alpha RMS is equal to about 0.2. And we can calculate here our weight for 5 over the weight for 6, and using this approximation, we get 1.22, which is pretty close to our exact measurement there. For a molecular system, n is not 10. N is much more close to Avogadro's number. So if we use a molecular system with n being Avogadro's number, the alpha RMS, the width of this distribution, becomes very, very narrow. It's about 10 to the minus 10. And so this ratio then is Avogadro's number, 6.022 times 10 to the 23rd, times 10 to the minus 10 squared, which is 10 to the minus 20, divided by 2. That's about 3 times 10 to the 3, or e to the 3,000. So we are about e to the 3,000, which is 10 to the 1,302 times more likely to see some dominant distribution compared to a different distribution. And this is not something that's way on the outskirts, right? This is something that's very close to the dominant distribution. And so we've kind of talked about this before, but what happens as we increase the number of objects that we're measuring, we greatly decrease the width of this distribution here, such that only outcomes very near the dominant distribution can be measured. Now, this is not to say that there is only exactly one configuration that can be measured that corresponds to the Boltzmann distribution. But what this is to say is that any distribution that is measured is going to be very, very, very similar to the Boltzmann distribution. So if we're talking about the distribution of gas molecules in the air, the Boltzmann distribution is going to correspond to an even number of molecules distributed throughout the air. So if we have a room, we would say we have 50% of the molecules on one side and 50% on the other side. Now, 50% of the molecules in a room, of the gas molecules in a room, is a lot of molecules. So we might see situations where there are 1 or 2 or 10 more gas molecules in one side of the room than the other. And these are all very similar to the Boltzmann distribution. But what we're not going to see is 51% of the molecules in the room being on one side. That would be a very different distribution, and we would get a weight that's much, much smaller, such that it's not possible or likely to be measured. And to put this kind of large number into perspective, right? What does 10 to the 1,302 mean? Well, if we want to compare this to time, we can go on our calculators and take the estimated age of the universe at 14 billion years or whatever it is, and then multiply that out to figure out that there's only been about 5 times 10 to the 26th nanoseconds in the universe. So this is, you know, way larger than anything we could possibly imagine, is 10 to the 1,302. And at this point, we can be pretty comfortable saying that if this is the likelihood of something occurring, is 1 over 10 to the 1,302, that will not occur, because we would need about, you know, if that were to occur in 1 nanosecond, we would need about that many nanoseconds for that to occur, and we have nowhere near that. What does all of this Boltzmann distribution, dominant distribution mean? To use this, we will use the central postulate of statistical mechanics. So this postulate says that every possible microstate of an isolated system occurs with equal probability. We've seen this before. Since all microstates occur with an equal probability, we are most likely to see the configuration of those microstates with the largest weight. This is directly analogous to the coin flips we've been talking about. I'm most likely to flip 5 out of 10 heads because there are 252 microstates that correspond to 5 out of 10 heads. As a comparison, there are only 10 microstates that correspond to 1 out of 10 heads. So we are about 25 times more likely to measure 5 out of 10 than 1 out of 10. Like we just saw in the past slide, in any molecular system, there would be such a large number of particles that we are really only able to measure that dominant distribution. So if we were to extend this to coin flips, we could talk about, like, what's the likelihood we get half a mole of coin flips out of 1 mole of coin flips being heads. And we would be very unlikely to see anything significantly different from exactly half a mole of coin flips. We can show this experimentally, because if we take a system that's at equilibrium and perturb it out of equilibrium, it always goes back to equilibrium. In other words, it goes back to that Boltzmann distribution. Because when we take it out of equilibrium, we're taking it to a state that does not have the dominant weight, and it's going to relax back into that state. This is known as the Boltzmann distribution law, and it can be used to describe the energy distribution associated with a chemical system at equilibrium. All we have left now is to determine what the beta parameter we used last class is. The beta parameter is a constant that determines how the energy affects the dominant distribution. We need to figure out what beta is in terms of something that is experimentally measurable. And ultimately, we know this is going to be related to the temperature, as we have used it last semester. To demonstrate the link between temperature and energy, we'll first consider how the weight of a system changes with energy. So we have 2 problems here to calculate the weight of a system of 10 harmonic oscillators with either 3 or 5 quanta of energy. So go ahead and pause the video now and try to come up with all of the different configurations for the system, as well as their relative weights. After you've done this, you should obtain the following results. For the system with 10 harmonic oscillators and 3 quanta of energy, there are only 3 possible distributions, like we saw before. So we can measure one where we have our 3 harmonic oscillators that are excited all on the same level. So we have 7 in the ground state, 3 in the first excited state. We could have 8 in the ground state, 1 in the first excited state, and then 1 in the second excited state. Or we could have 9 in the ground state and then 1 in a third excited state. And when we're doing this, what we're doing is taking 3 quanta of energy and figuring out all the different ways that we can arrange the energy. We've done some problems like this in class. In total, we can add up the weights of these individual configurations to get the total weight of the system at 220. For the system with 5 quanta of energy, we have much more options. We could have 5 molecules in the ground state and 5 in the excited state. We could have 6 in the ground state, 3 in the first excited state, 1 in the second excited state, 7 in the ground state, 1 in the first excited state, 2 in the second excited state, and so on. We could have these 6 different configurations, and they have much larger weight. So adding these together, we have a total weight of 1,912. So what we can see is that by adding energy, we have increased the weight. So the weight increases with energy, and this is true in general. As we saw on the slides, there is a connection between the weight of a distribution and the energy. And we already know we can relate the weight of a distribution to this beta parameter. So what we're going to do is connect those two here and ultimately show that this beta parameter is somehow related to temperature. And we'll start by investigating the derivative of the natural log of the weight. We'll start by investigating the derivative of the natural log of the weight. So in the last class, we saw that the natural log of the weight can be written as the natural log of n factorial over the product of all of our a sub n factorials. And we could boil this down to the natural log of n factorial minus the sum of the natural log of all of our a sub n factorials. Now what we want to do is take the derivative of this with respect to the occupation number. So we can take the derivative of the natural log of weight with respect to occupation number a sub n. This gives us a derivative with respect to a sub n of the natural log of n factorial. And then we have a derivative of the summation term over here. Now, the natural log of n factorial is actually a constant. So the derivative of this here is simply equal to 0. And then we have this over here. We'll use Stirling's approximation. We'll take the derivative now of the sum of a sub n natural log a sub n minus a sub n. And when we do this, when we take this derivative, we end up having simply this sum over n of the natural log of a sub n. And so with this, we can say that the derivative of the natural log of the weight is equal to the sum over the natural log of all of our occupation numbers a sub n times dA sub n. We next use the Boltzmann relationship to introduce energy. We can state that the ratio of a population a sub n to its ground state a naught is simply equal to the following. So a sub n, we derived this before, is equal to n e to the minus beta epsilon n over q, the partition function. And for the ground state, it's n e to the minus beta epsilon naught over q. Now, what we often do, and we've already seen this, is assume that the ground state has an energy level of 0. If that's the case, then this beta e to the minus beta epsilon naught term is 1, and then our n's and q's cancel. So this ratio is simply e to the minus beta epsilon n. If we don't assume that it's 0, right, we get what we got last semester, we would have e to the minus beta delta epsilon here. But we can, if we assume it's 0, we can just set that to epsilon n. What we can do with this is then say, okay, well, we have our an. Our an is therefore equal to a naught e to the minus beta epsilon n, and we can plug that into our expression for the natural log of an. So the natural log of an is then the natural log of a naught e to the minus beta epsilon sub n, and we can separate this with log properties to say that this is equal to the natural log of a naught plus the natural log of e to the minus beta epsilon n. And if we have the natural log of e raised to something, that's simply that something. So this becomes the natural log of a naught minus beta epsilon n. We can plug this back into our earlier expression for how the weight changes. So the derivative of the natural log of weight was equal to the sum of the natural log of a sub n times dA sub n. We now know what the natural log of a sub n is. So we can say this is the sum of the natural log of a naught minus beta epsilon n dA sub n. And we can rewrite this as two sums. We have the negative natural log of a naught times the sum over n of dA sub n. And then we have plus beta times the sum over n of the energy times dA sub n. You may be wondering why this is negative and why this is positive, and that's because in my derivation up here, I did miss a minus sign. So we need a minus sign in all of these, and this is where that negative comes from. So we have that the derivative of the natural log of the weight is equal to the negative natural log of a naught times the sum over all of our occupation numbers, the change in those numbers, and then plus beta times the sum of our energy level times the change in occupation numbers. What this is here, this is the sum over the change in all of our occupation numbers. We can't gain or lose any material in our system, so this sum is 0. There is no net change in the occupation numbers. And then we can simply write this here, the change in our natural log of work, as beta. Now, what this term is here is the energy levels of all of our systems times the changing in occupation numbers. So this is dE, the change in energy of our system. This gives us a relationship between weight and energy. To wrap all this up, we want to relate the beta constant that we have here into some measurable property of the system. So what we're going to do is consider two systems that are in internal equilibrium and that are brought into contact with each other. So let's say we have one system, maybe it's a metal rod and it has a certain weight. And then we have a second system, a second metal rod that has its own weight. And what this would mean, right, these would be at different temperatures. Now, if we bring these two systems into thermal contact with each other, what will happen? Well, if they're not at the same temperature, we expect them to reach the same temperature. So they are changing in some way. Now, if they're changing, they're reaching a new equilibrium. What that means is that the product of these weights, so Wx times Wy, the new weight of the system as you bring it together, is changing. And if it's changing, it must be increasing. So the change in the product of our two weights here is increasing as it goes to equilibrium. It's finding its new dominant distribution. We can evaluate this derivative as follows using the product rule. So we can say that the weight of state y times the derivative of the weight of state x plus the weight of state x plus the derivative of the weight of state y is greater than or equal to 0. And we can rearrange this to have dwx over wx plus dwy over wy, having this being greater than or equal to 0. And if we have dx over x, that's simply the natural log of that. So we can finally say that we have the derivative of the natural log of the weight of x plus the derivative of the natural log of weight y, and have that being greater than or equal to 0. We know from the expression up here that the derivative of the natural log of the weight is simply beta times dE. So what this gives us then is beta x dEx plus beta y dEy is greater than or equal to 0. In this case, what we're doing is bringing two, say, rods into thermal contact, two systems into contact with each other. Therefore, we have two of the following statements: the change in the energy for the x half of our system plus the change in energy of the y half of our system must be equal to 0. Energy flows from one direction to the other. So we can say then that dEx is equal to negative dEy. We can plug this in up here to find that beta x times dex is then equal to beta y, or plus beta y, times negative dex. With this, we can cancel out our dex and find that beta x minus beta y is greater than or equal to 0, or that beta x is greater than or equal to beta y. What we can do in this case is choose that dex is positive. Now, this is arbitrary, but we could have done the same thing with the other direction as well. So dex is positive, which means energy is flowing from y into x. What does that say about the temperature of y and x? Well, if energy is flowing from y to x, the temperature of y must be larger. So we can say that the temperature of y is greater than or equal to the temperature of x in this case. For both of these statements to be true, for bx to be greater than by and ty to be greater than tx, they must be inversely related. So we know at this point that beta is proportional to 1 over t, and if we do some experiments, we can come up with this proportionality constant being Boltzmann's constant k. So beta is equal to 1 over kt. We've already seen this result last semester, and we can look up Boltzmann's constant in the back of our book. A common unit for Boltzmann's constant, especially as we will be using it in statistical thermodynamics, is in units of inverse centimeters rather than joules per Kelvin. And so if we do this, our Boltzmann's constant is equal to 0.69503,423 inverse centimeters. If we multiply that by room temperature, 298.15, this is inverse centimeters per Kelvin. And if we multiply this by 298.15 Kelvin, we get approximately 207 inverse centimeters. So with this information in hand, we can now move forward in the next couple of lectures to determine the probability of a molecule being at a certain energy level. And you'll remember doing this last semester as well. We can compare our energy to KT, and if it's similar to KT, it might be approximately continuous. If it's very much larger than KT, we're not going to observe a continuous spectrum. And we'll go into this in more detail in the coming lectures. To conclude this section, every distribution of molecules, so every microstate, is equally likely to occur. Configurations according to the dominant distribution have many more microstates that make them up, which gives them a larger weight. And these distributions are the only ones that are likely to actually be measured or observed. We'll see, especially in the coming lectures, we started to touch on it here, that molecules are more likely to be at lower energy than higher energy. This also affects their likely configurations in microstates. And we can use the Boltzmann distribution to predict the probability that particles will be at certain energy levels. Now, to put this into sort of a more quantum mechanical context, we can use the Boltzmann distribution to predict the coefficients of the wave function, right? So we can't necessarily say that 20% of my particles are at energy level 1, but I can say that my particles are 20% at energy level 1 in their wave function. I can build up these wave functions using the Boltzmann distribution. In the future, we're going to go and start to actually apply this to real degrees of freedom for molecules.